Afternoon, everyone. Welcome to the show and tells. We'll just wait for a few minutes whilst we admit people.
Afternoon.
Do you want to make a start, David?
Yeah, sure. Welcome, everyone. So we're going to get started with the next session. These are all recorded, so we'll be running through the introductions again, but then we'll move straight into the presentations.
The Strategic Innovation Fund is investing £450 million in energy network innovation, because the challenge of rapidly decarbonising our energy networks is enormous. But we can do this. With collaboration, we can make the leap. A giant leap together. We need the bravest, brightest, boldest change makers from across the world to work with Innovate UK, Ofgem and the Strategic Innovation Fund to create the energy networks of the future. The best ideas targeted at the most pressing challenges that reduce emissions and save consumers money. Join us now. Take a giant leap together with the Strategic Innovation Fund at ofgem.gov.uk.
Hello, and welcome to everyone for joining us for what promises to be another insightful set of show and tells covering the SIF Discovery, Data and Digitalisation Challenge projects. This afternoon, we'll be focusing on asset monitoring and analysis projects. Firstly, a huge thanks to all the participating energy networks, especially the innovation teams, but also to all your partners who've worked extremely hard over the last few months putting together and delivering these projects. We appreciate the way that you've embraced this new mechanism head on, and will continue to work with the energy networks and our wider stakeholders to refine and improve the SIF process in a way which achieves maximum impact. The SIF has two simple objectives: to deliver net zero at lowest cost to consumers and turn the UK into the Silicon Valley of energy. The energy sector is obviously under immense pressure currently, and no one is feeling that pressure more than consumers. For us, this underlines the importance of innovation, and we believe that innovation can play a central role in making the UK the best place in the world to be an energy consumer and the best place in the world to be an energy entrepreneur. There are three pillars to the SIF. The first is strategic alignment with other funders and sectors, helping us to bring together various funding programs and work across silos. The second is delivering fully in Agile. That's the challenges, the discovery alpha beta mechanism, and the way that the SIF operates as a unit. The third pillar is around commercialization and driving innovation to become business as usual as quickly as possible. Development of new products, processes and services that deliver benefit to people and drive down emissions is the central mission of the SIF. No single organisation can achieve these outcomes alone, so we've termed the process a giant leap together. Networks, infrastructure owners, regulators and government will need to work together on key problems to achieve success. Giant Leap Together has 4 periods across the year, where together we focus on different aspects of innovation development. These include challenge setting, and you'll see that we've recently released our round 2 challenges, which will launch for network applications in September. Targeted ideation, where we point great ideas in the direction of networks and broker collaborations. Incubations, where the networks can really start to build their awards-winning consortia. And finally, acceleration, where the challenge is open and we join the ENA, Ofgem, BEIS and others in hosting the first ever UK Energy Innovation Summit on 28th and 29th of September in Glasgow. The round 1 discovery projects that we're going to hear from are now in acceleration. The teams have been working flat out to put the pedal down on innovation development. It's been an intense start to the SIF programme. We need to focus as much time as possible on delivering ideas, taking risks, and ultimately delivering value to consumers. The aim of this first phase has been to learn fast, pivot quickly, and fail small. Some of the projects may have disproven their original hypothesis or discovered unknown barriers during their discovery phase. These are really valuable findings too. It's better to learn these things earlier, take a different route, or return to base camp and replan whilst it's still possible to do so. Embracing positive failure is an important part of the SIF. Finally, I'd just like to thank the Innovate UK team and the innovation team and the PMO who've supported and worked so hard to put all these sessions together. We'll now start moving on to the digitalisation rounds of challenges. And I'd just like to talk for a few minutes before we kick off the projects about what we're looking for. The aim of the Data and Digitalisation Challenge was to deliver the next generation of user-driven digital products, services and processes, which span all of the energy networks, industries and government. Some of the themes that we're really looking at focusing on included data monitoring, quality and collection, and I think we'll see some of that in the upcoming projects. Developing, enabling digital products which support the other challenges in their objectives. Unlocking data access, interoperability and insights for third parties, and improving efficiency, security and resilience of the energy networks. We've got 2 sessions this afternoon. The first is a group of projects which are all being delivered by National Grid Gas Transmission, and we'll have a short break before moving on to the last 2 sessions, hoping to wrap up with a Q&A session by about 3:20. I do ask you, please be liberal with asking questions in the chat box. If you put them in as the presentations are going on, we'll then come back to them and talk around them during the Q&A session and after the 3 presentations. So if you're ready, Peter, I'll hand over to you for the gas analyzer systems for hydrogen blends project.
Brilliant. Thanks so much, David. Hopefully you can all hear me okay. If you just take us on to the first slide, please, that'd be great. Thank you. So yeah, good afternoon, everyone. Thanks for joining. So I'll be sort of taking us through the gas analyzer systems for hydrogen blends discovery phase today. My name's Peter Martin. I work in the hydrogen innovation team at National Grid, and I'm joined today by Martin Cross, one of our other partners on the project from Design Core, who will also be supporting me. Could you take us to the next slide, please? So we'll kick off with sort of the problem that we're looking to sort of start solving with this discovery phase. So today's networks are relatively homogeneous in terms of the gas mixtures that we transport, for which current gas analysis systems are deemed acceptable. However, in a future hydrogen network, there is potential for more significant variations in the blends of gas across a network. Therefore, there's likely to be a need for a much larger number of gas analyzer sensors on the gas networks that can accurately measure the energy value and content of blends of hydrogen, are quick to respond, cheaper than the solutions today, and are able to effectively network through the Internet of Things to allow effective data sharing across industry and then also consumers. This discovery phase project is focused on the feasibility of using fuel cell sensor technology to carry out the required gas analysis in a hydrogen network whilst connected to the Internet of Things to help solve this challenge. Next slide, please. So I've mentioned that this project has been a collaborative effort between partners Design Core, Gas Transmission and Metering, and then also Cadent Gas. The overall objectives of this project have been to benchmark the fuel cell sensor capability against other existing gas analyzer systems that are out there, and to assess the technical and regulatory barriers and opportunities involved in the adoption of a new technology such as this on the gas network. And also, this is very important with within the data and digitalisation theme, is to also demonstrate the feasibility of Internet of Things connectivity through the use of this technology. Just on the side there, I've sort of listed some of the work packages that have been undertaken in the discovery phase to give you a bit of an overview. So work package 1 was a feasibility design stage, which built on use cases that were collected during the project to determine an appropriate system architecture for the technology. And then moving on to work package 2, involved solution prototyping and fabrication, and then putting together a lab and software systems test plan, which then feeds into the next work package, which was the rig testing of the prototype fuel cell gas analyzer against different hydrogen blends in natural gas, and matched against 2 gas chromatographs which were lent to Loughborough University by National Grid. And then finally, the work package 4 was focused on putting together the technical report produced with those results from work package 3, and then the intended plans for the alpha stage. So hopefully that gives you a bit of an overview of what the discovery phase has been looking to achieve, and then I'll now hand you over to Martin Croft.
I don't know if you can hear me.
Yeah, we can hear you now, Martin. Yeah.
All right. Okay. Can we have the next slide, please? Hello, my name is Martin Croft. I'm Managing Director of Design Core Limited. We've been working with National Grid to look at this discovery phase. So we know that the current analyzers that are out there are really not fit for purpose, as they for the net zero goals. They specifically are very slow to operate. You tend not to get a reading for 4 minutes or longer if you set them off. They're very expensive, not only for the actual kit, but also the infrastructure and how they get installed. And their understanding at the moment from the supplier is that 2 units would be required, one for the normal hydrocarbon mix, and also another unit for the hydrogen mix. I haven't integrated it into a single unit as yet. But also, more importantly, for this particular project, they are not connected to the internet and Internet of Things. So we know that blended hydrogen networks, as Peter was saying, will require single, faster, cheaper sensors and a new digitized data architecture. So what we're doing in designing a new sensor is designing it with these things built in from day one. So the fuel cell sensor is a blended gas sensor that has been developed as a single unit, which can do this to give those accurate gas readings in near real time. So you don't have to wait 4 minutes and have 4 minutes of gas disappear down the network and then suddenly realize actually that's the wrong kind of gas that you should be supplying. The project is aimed to, this discovery phase project is aimed to show that the fuel cell sensor data can help the gas transmission and distribution networks with this real-time control by looking at a number of different use cases and talking to people about the different ways that the sensor or the gas quality could be collected and used, and seeing how they would benefit from that. Next slide, please. So we're going to take these into two main groups of use cases. One is from the national transmission system. So obviously the gas national control center is number one and has always been taking the data currently, so they would need the data in the future. But then there is a number of new use cases for the transmission system that would need some kind of gas quality data. We've deblending or blending and deblending requirements in the network. If you're taking hydrogen in or trying to extract hydrogen, then that would be a good place to need to look at the quality. As would be an injection of hydrogen in the network. That would also affect the gas quality and the energy content by injection of hydrogen, as hydrogen has a lower energy content. Compression control is another area where we know that the compressors will need to operate slightly differently in a blended hydrogen environment. And so again, having an indication, an accurate and real-time indication of how the blend is being mixed at the time when it hits the compressor could help control that compressor and provide it with a much more effective and efficient way of doing the compression. We also know that when we start to put hydrogen down to some of the steel pipes that we have around the network, that there will be some embrittlement problems that need to be controlled. So knowing exactly how much hydrogen has passed a particular part of pipe might be very useful to help monitor and control that embrittlement on those assets. Having simpler connections as well would be useful from the biomethane connections that are around about 100. You could expand that 10 times quite easily in the next 10 years or so by adding the hydrogen connection. So having a simpler connection technique with lower cost sensors would also help. And back to the National Gas Control Centre thing, then obviously there's a billing aspect of this, which needs to be considered in terms of how the gas is billed and what energy content is in it for customers. And then looking at the other side, on the distribution side, we were speaking with Cadent on this and looking at what they were saying in terms of the blending and how it might operate. Although they believe that there is a decision to be made at some point in the future which says how much blended gas gets to them, or whether they try and go 100% hydrogen on a step-by-step basis and flow that through the network. But assuming we are going the blended route, then zonal sensors would be very useful for them to look at the actual amount of hydrogen and the energy content throughout their network, as well as some of their industrial and commercial customers, where bespoke billing would be useful for them to actually know what energy they're getting. And really, those commercial and industrial customers would also like to know the energy content for their own processes. So if a process is actually very dependent on the energy content or the actual mix of gases within there for the quality of the product that's coming out from the industrial or commercial customer, then they as well would like to know immediately what the kind of energy content or the amount of hydrogen that they're actually having to cope with in their industrial processes. So that's also very important. And then from an auditing point of view, there's a lot of companies out there that are being judged by the stock market and others by how green they are, and they would like to audit their whole business, and the energy content going into that business needs to be decided on in terms of how green it is, so they can add that into their calculations on how green a business. So we would know definitely for certain when a particular business meets their net zero goals, because they can count that 10%, 20% of hydrogen in their calculation for the energy that they're receiving. Again, also the billing aspect from Cadence perspective, or the distribution networks. And then there's the Joe Public and the standard consumers and their smart meters. You know, they want to know as well what they're getting in terms of the energy content and being billed correctly, but also how green is that consumer, and that is a really important publicity thing as well to keep in mind, that these consumers need to know how much hydrogen they're being asked to use in their homes. Next slide, please. So let's look at the activities that we've done. So we collected the use cases over a number of different parts of the businesses, and we've done some basic analysis on those, but we know that there's a lot further in-depth analysis of those needed in the alpha and beta stages. And that's something that I'm sure Peter will come on to later. But we also looked at the current data architecture, that the chromatographs, and also proposed a new IoT design, which would be very light and flexible and applicable to many different sensor designs. And to prove that it was fairly flexible and fairly easy to implement, we did this on a fuel cell sensor and added a connection to the Azure-based platform, the one that National Grid currently use, but obviously it could be equally applicable to AWS or any other data cloud platform where you're looking to provide a secure wireless IoT connection via a wireless VPN, low power WAN network to connect what is critical infrastructure connections, but in a very resilient and cyber secure way. And these networks are used a lot by the police and military and a lot of other industries around the country. And so it does seem unusual that they're not starting to be rolled out in mass production in the gas network as well. Also, one of the work packages was to complete the assembly of the fuel cell system module and integrate all the hardware, software, mechanical and thermal elements of that system together with Loughborough University. And now we have a complete system running under our control that we can get data from. And as part of that was setting up the Loughborough University lab with the gas chromatographs. So now there is a complete lab set up with bottled gas to be able to test lots of different ways of mixing gases and checking that they match the gas chromatograph output, and then we can check that they match the flow that the actual fuel cell sensor is using. And these were, we got the first few test results in just in time. 2 months. It's quite tight program, and they fairly well matched the chromatograph results. Well, actually, the fuel cell sensor matched our flow controller data, but the gas chromatograph was slightly out. But we still haven't gone through the analysis of those results yet, and those will be over the next few months and during the alpha phase to show how the things are are related in the data terms. And also we did some benchmarking of other gas analysis systems that are out there as well. Next slide, please. So what have we seen from the benefits of doing this discovery phase? Well, we've discovered that there are a lot of use cases out there for gas sensing, much larger than we first envisaged in our application when we put the discovery phase application in. So those solutions now need to be examined. So we can see how they would be most serviced cost effectively, so that the right use case gets the right sensor in the right position in the network. Then there is the fact that blended hydrogen networks will be deployed and they will need faster and cheaper sensors in a greater number of those applications. That slow and expensive sensors are not applicable. And the cost reduction can be enhanced by the use of new digitized secure data architectures. And this is obviously something that Innovate has in mind is you need to think of how can we save money. Okay, there's going to be a lot more sensors out there, but if you can save money by having them a lot cheaper, then you'll have a much better network at the end of the day, and one that's more innovative. And then we've also seen how the the fuel cell sensor gas analyzer has been developed from a single sensor to give accurate gas quality readings in near real time with IoT functionality built in. So it's not an add-on to the sensor. It's made as part of and integrated into the whole system, and at less than 1/20th of the cost of the existing system, how it's actually set up. And then finally, we're looking at how the project can help with that control of real time, and how that data can be used by different customers and different users. So speeding up the transition to a greener gas network and achieving net zero for the UK. Next slide, please. Over to you, Peter.
Brilliant. Thanks so much, Martin. So just sort of close off with sort of our plans for the alpha stage of this project now. I think we've got some quite exciting plans for the alpha stage. We've made the decision to combine this discovery phase project with the other hydrogen metering SIF project, which Chris will be taking all of us through shortly. The reason for this is that for us to be able to continue to effectively measure and manage the energy balance of our networks with blended gases, we'll need flow measurement and energy measurement systems to be able to function together. Therefore, we've decided to bring the two elements together in one project. I'll sort of just go through some of the key activities that are listed there. So carrying on the work from the other hydrogen SIF project, hydrogen metering SIF project, which Chris will go over, and sort of looking at comparing the capability of current existing hydrogen metering technologies in terms of the capability matrix to enable us to do some testing in the beta stage. And then another work package carrying on the work that we've been doing within this discovery phase SIF in terms of the gas analysis side of things. I think it's really important that we do continue to do work to look at what else is out there on the market, what are all the potential options for analysing hydrogen blends, as well as continuing to develop this fuel cell gas sensor technology. And I think sort of the key thing about this next alpha stage, and the most important bit for the data and digitalisation aspect, is bringing the two elements together. So you see their work package for the end-to-end system design. So it's how in the future with these two, a metering system and the gas analysis system, how do those two work together whichever location is required, what data systems are we going to be needing to disseminate and distribute that data to where it needs to be, whether that's industry or consumers, and making sure that it's sort of agnostic as possible to bring in whichever technology we think can do the job, meet the requirements. And then the other thing that we're looking at as well is the commercial impact of these new developments, so taking into consideration potential GSMR changes or Cadence future billing methodology as well. So there's that link there. And then something else I'm sure Chris will touch on as well is we're looking to sort of have out of the back of the alpha stages, not only sort of some test plans for beta, but also the design of a new hydrogen measurement test facility. So I think that wraps up our sort of the plans for the alpha stage. I look forward to any questions you may have at the end. Thanks very much.
Thanks both, appreciate that. A reminder that if you do have any questions on these projects, pop them in the chat and we'll go over them during the Q&A session at the end of this cohort of presentations. And the next project is hydrogen metering. So if the team's ready, should I hand over to you, Chris?
Yeah, I'm ready. Nice one, thank you. Yeah, if we jump on to the next slide, please. Brilliant. So yeah, I'm Chris Wood. I was the lead for this hydrogen metering discovery project. I'm going to be joined with my colleagues Claire Ashton from DNV and James Blakey, who's also part of gas transmission and metering, which is currently part of National Grid. If we go to the next slide. So I just thought it's useful setting a little bit of context, really. So why are we looking at hydrogen metering, or why have we got questions around how metering would work under a hydrogen environment? Well, the first requirement is obviously one of the most important for us to manage networks effectively and for us to make sure that consumers have got confidence that the bill that they're receiving is accurate. We need to make sure that that's underpinned by evidence-based work. So the type of metering technology that we use has been tested. The type of gas analysis equipment, as Peter said, has been tested under various different types of hydrogen or hydrogen blends. We know that hydrogen is obviously a key solution in part of the transition to net zero. And I think, again, just to set the scene, if you look at a comparison of a unit volume of hydrogen against a unit volume of natural gas, within hydrogen, there's a third less energy. And therefore, for the consumer to get the same amount of energy they would under natural gas, you need 3 times as much volume of hydrogen or 3 times as much flow. So therefore, you've got an increase in potential flow that's coming through the meter. Build into that as the fact that hydrogen is less dense and the smaller molecules, then it's not a foregone conclusion that the current technology that we use today to measure natural gas will also work on hydrogen. We need to look at that, and we need to ensure that it can deliver the same accuracy and performance as it does today under natural gas. So we go to the next slide, please. So again, a little bit more context. So we're looking at the whole gas transportation value chain. So what we mean by that is gas transmission, which is your national system, your distribution networks, which obviously deliver gas on a regional basis, and then where the network ends, which is typically at the emergency control valve, to where the consumer pipework starts, is typically your end consumer metering installation, and that's used for billing the volume of gas that's being used by the end consumer. We reckon there's around 600,000 metering installations across the UK, across all the networks and industrial and commercial metering installations as well. It doesn't conclude domestic, which is about 26 million. So this project was focused primarily on I&C and network installations. And we estimated at the beginning of this project, if you just changed out the meter box for a brand new meter using today's technology, and that will cost around £439 million in excess of that. That's not building into account the labour costs, the changes to the installation. And actually, if hydrogen metering is more expensive, then that figure is going to be astronomically higher than what we see there. And the Venn diagram on the left is really just demonstrating why we're looking at the gas transportation system as opposed to just one particular element. And it's because that the technology that we use is very similar. So while there are different use cases, at the different points of the network, the type of meters that we use tend to overlap and we tend to share different similar types of makes and models and manufacturers, etc. If we go to the next one. So in terms of what we were doing in this discovery phase, it was really a feasibility study to, I guess, test the value of the project in the eyes of industry stakeholders, as well as determining what the requirements could be from each of those stakeholders. So what we started off with was actually a hypothesis, which we said, right, what we want to do is build a number of metering installations from both repurposed metering equipment to test existing technology and new equipment as well to perhaps test new and different types of metering. And we want to operate them at hydrogen and hydrogen blends and make sure that they fully replicate the metering facilities that exist today on the gas transportation system. And by doing that, we can get a deep understanding of how metering is going to operate on a hydrogen network or a hydrogen blend network. And that's ultimately going to give consumers confidence in the data that they get and the billing that they get from that, and make sure that we can manage networks effectively. So we looked at 4 elements. One was looking at stakeholders, again, to test the value and understand requirements. We looked at the supply chain to understand what technology is out there today. We had a look at industry standards as well, which are underpin the physical build of some of these installations. And then where we got to at the end was looking at different use cases, different types of assets to test, different tests and specification. So the project team, as I say, was gas transmission and metering, which is part of National Grid, Northern Gas Network support from a distribution perspective, DNV were our technical partners, and IGEM were there to support with the industry standards. If we go to the next slide. So looking at stakeholder requirements, so it's quite an intense piece of work. So we spoke to about 46 people across about 26 different organisations, and they included regulators, BEIS, Ofgem, right through to metering manufacturers, energy users, energy transporters, consultancies, some of the hydrogen projects out there today. And again, the opening question was, after we pitched what the project was around, was, you know, is there value in this? And everybody came back and said, yes, 100%. There is value, and that this is a really important piece of work to do. As well as just confirming the value, what we outputted was actually some of the things that the stakeholders wanted to look at existing assets, so you know, so we can understand repurposing costs. As Peter mentioned earlier, we also asked the question on gas quality and gas analysis technology as well, so that we could understand not just the measurement of flow or the measurement of volume. We could also include the energy calculations, and stakeholders also talked about in a hydrogen world that traceability of hydrogen was important to them, and understanding the purity as well. Making sure that we do these tests in the real world environment, or as close to real world as we can do, was important. And looking at industry standards again was key, which was one of the other work streams. But also that this project could be used to look at not just current technology, but also new technology, and potentially, for the gas network at least, innovative technology as well. And a final point, which I think was you know, a little bit outside of what we'd originally envisaged the project to be, was about competency framework development. So particularly in the metering world, the end consumer metering world, it's quite a competitive industry with lots of different companies, lots of standards dictating how people need to become competent to fit and install meters. So again, having this facility up and running on hydrogen could support that framework development and help with standards and other frameworks as well. So if we go to the next slide, and James, you want to take it from here?
Yep, hope you can all hear me. As part of the project, we went out to the supply chain and did an assessment, and we sent a request for information out to 24 organisations. Got 16 responses back, and this was from a mixture of existing manufacturers that are used, we use quite a lot within the industry, and then some startups as well. There's some encouraging new technology to the gas industry, probably not new to other industries, that's being developed that was quite interesting. So I had nuclear magnetic resonance meters and some Coriolis meters as well. And it's also quite an interesting one that a lot of manufacturers are now out there. There's a range of new products being under development. So in the next sort of 18 months, 2 years, there's a lot of products they're bringing on. And there's also been really good progress by the supply chain, looking at existing products. Are they suitable? Are they working? What blends they'll work with? and they've really done a lot of work so far, and there's quite a lot of information that came back on that. Some of the gaps that we did identify though was with the sort of limited areas. So there is product coverage, but maybe 1 or 2 products in that area. So it's one where going forward some work will be needed done with some manufacturers to see what they're looking at in the future. Next slide, please. Also, as part of the project, we did the industry standards review. So this was looking at, in joint with Ofgem and all the partners, looking at the standards that will be used in metering installations across all the different streams, so transmission, distribution, and in our world, it's the INC metering. So one of the bits that we looked at was where there'd be gaps. So what gaps are there? Where would we need to look at going forward, and where would this project sort of feed into that? So ones that did come up was meter suitability across higher flows and pressures for measuring hydrogen, so just seeing how the impact of hydrogen on them higher flows would impact the meters. Ancillary equipment, this is everything sort of beyond the meter that's connected to the system. So it could be valves, slam shuts, control systems. So how will they be affected by hydrogen blends as well? Will they work? Will there be different characteristics? Will maintenance need to be changed on hydrogen and blends? Will it affect that? So that was one area where there's some gaps to be looked at. And also the acoustic performance. So under the new higher flows and higher pressures, how will that impact the installations? And also on the velocities, so the new energy requirements that are different to natural gas, how will that impact the systems as well? And the one that really come back to us as well from some of the stakeholder engagement was on the repurposing standards. So there's been some work done so far by Ofgem, but really trying to get a standard out there for the industry to use, so it gives really good in-depth information and data on if you repurpose an installation, what's needed, and how we can do this as an industry to trip best costs from the installations you already have in situ, rather than putting new installations in. Next slide, please, and that's over to Claire.
Hi. Having pulled together then the stakeholder information and the supply chain and the standards review, we tried to kind of review where we got to and see if we could condense down all the information into a kind of single question or scope to move forwards with. And that's the statement that you see at the top of this slide. It became apparent that there was a need for work both with hydrogen blends and for 100% hydrogen, and that the focus of where we want to take this project is on measuring volume and energy, and to take that into as real world a situation as possible. So that's our kind of statement that we want to use going forwards towards the alpha stage. We then tried to kind of take this out into the asset types and the types of testing we'd want to do, and you can see those listed on this slide. As Chris has mentioned before, we're looking at everything from transmission down through to industrial and commercial users on a low pressure network. So there's quite a range of meter types, gas analysis equipment and ancillary equipment that we see needs to be included within this project. And we want to do a lot of different types of testing. Obviously, there's a focus on accuracy to allow the measurement, which is the key focus. But there's a lot of other testing that needs to be done on safety and on sort of life cycle of assets with hydrogen being used, as well as also the gas quality equipment and also things like flow computers and some of the calculations that will need to be done. From this, we started to work up a functional specification. So at the moment, this is more just a list of factors, but we hope to take this forward in the sort of alpha innovation stage, if that's possible. So we're looking at all the sorts of factors that we need to take into account when carrying out testing. What we do want to bear in mind with this as we look to test and develop this in this area is that we want improvements. We want there to be improvements in data management and in digitalisation. So it's not just business as usual, but in actual fact, we're looking to make improvements beyond what there already is as well as part of this project. The next slide, please. Oh, could we have the next slide, please? Thank you. No, back one, please. Thank you. Yeah, so we pulled these thoughts together, and we actually had a site visit as part of this project and went to have a look at the Future Grid and H21 facilities up at Spade Adam in Cumbria. So Future Grid is a high pressure test facility, and H21 is more on the distribution network. So we've got different pressures, different pipe sizes. We had a look at both of those. And there is already the capacity at Spade Adam to store hydrogen and obviously to service those two test facilities. So that's what makes this site ideal as far as we're concerned, that there is already the capacity for using hydrogen there, and there are already a lot of network assets that we can repurpose. We will need metering installations, and we've already started to look at where we could obtain those from, both from the transmission network and from other installations that National Grid metering may have available. And like I said, we are looking to cover the full range of pressures, to cover through from transmission down to low pressure end consumers. So at the moment, we're not quite clear whether this will be one test facility with decreasing pressures, or whether there might be more than one test facility linked into different parts of the existing facilities at Spade Adam. So what we're proposing here will meet the functional specification and the stakeholder requirements. And the next phase that we're looking to develop will be to work this up more specifically and to design it more thoroughly. Next slide, please, and back to Chris for some conclusions.
So thanks, Claire. Thanks, James. So yeah, just to sum up the project, I mean, we kind of come to a number of conclusions actually, but these are the most pertinent ones. So, you know, what we want to make sure is that when we do build the facility, as Claire says, to be determined exactly how that would look, but we want to make sure that we're testing not just the meter. We're going to look at the installation as well, so the ancillary equipment, the sensors, the pressure regulators, the filtration, etc., because that all affects the way that the meter measures the gas that flows through it. So that's important to bring that into the scope. We talked quite a bit about the stakeholder requirement to bring in gas analysis. So we want to make sure that we can do accurate energy calculations, but also perhaps some use cases in a pure hydrogen network, which stakeholders are interested in. So traceability of where the hydrogen has come from, the purity of hydrogen, etc., is something that we want to start to have a look at. As Claire mentioned, we'll do a number of tests on different metering technology and different types of assets as well. And there is this opportunity as well, and Peter touched on it in the previous presentation about actually, if we do build this at Spade Adam, we've essentially got a mini gas transportation system up there which can replicate what exists today, and it might give us the opportunity to look at the end-to-end measurement system as well, which might lead to more effective network operations and more efficient ways of delivering hydrogen blends and hydrogen to the end consumer. So that's something that we're really keen to take forward. We know that there is metering technology out there that has been used on hydrogen. That isn't necessarily new, but we've got an opportunity here to test whether it's suitable to use on the gas network, and whether that can be used in, I guess, jointly with existing technology, or whether that's something that we would take and it would be more efficient to use. And ultimately, as the high-level question demonstrated, the project is going to determine what's the most cost-effective and most best way to measure energy and flow in a hydrogen network and a hydrogen blended network. So we've gone to the final slide, please. So Peter talked about this in depth in his presentation, but it's just to emphasize what we will do in the next phase, in the alpha phase, is combine the gas analysis work that Peter and the team did there into this as a whole sort of hydrogen and gas analysis project. We'll carry on doing the work which would define the design of the installation that we want to build, but obviously there'll be a key gas analysis requirement in there as well. And then this piece about the end-to-end system design as well is a great opportunity for us to really look at the whole network and how we could look at the data that then perhaps the measurement systems will produce, and that's going to aid in the digitalisation and the efficient network operation. And the commercial package there is to support some of the billing methodologies, etc., that are being developed for hydrogen blends and hydrogen. And as you can see there, the number of partners is increasing, so it is turning into a larger scale project. But given the fact that the stakeholders overwhelmingly saw criticality and importance in the project, and the fact that it's bringing in some of the extra factors that they specified as well, it's just going to really help us understand, you know, the data that we will need in future networks under hydrogen, as well as supporting the digitalisation of the system and making sure that we can run our networks as effectively as possible to deliver the gas to the consumers in the way that they need it to. So that's it from us. Thank you for your time.
Thank you very much for everyone who presented in that session. We'll now move on to the next project, which is the high NTS pipeline data set. Back over to you, Peter.
Brilliant. Thanks so much. Yeah, so we're now going to talk through the high NTS pipeline data set and discovery phase project. So as I said before, I led in this project from a National Grid perspective from the Hydrogen Innovation team, and I'm joined today by Adrian Horsley, who's representing one of our partners for this project, the Rosen Group. So if you could move on to the next slide, please. So what is the problem that we're looking to solve with this project? Well, it's very obvious that the existing national transmission system and local transmission systems were designed and built to transport natural gas, which when you compare it to hydrogen, it's relatively inert. For us to consider repurposing our networks for the transportation of hydrogen, there's going to be new additional pipeline integrity considerations that are going to have to be made above what we currently do today on a methane service network. Hydrogen has the potential to degrade pipeline material properties, meaning that anomalies may have reduced critical sizes, or anomalies usually not as much of a concern in natural gas service, such as cracks or hard spots, may present a new potential concern. Therefore, before repurposing our natural gas networks for hydrogen, we must determine the additional data and tools that we're going to require in order to assess the pipeline's readiness for hydrogen conversion. Move on to the next slide, please. So, give you a bit of an overview of the discovery phase project then. So the project has been a collaborative effort between partners Rosen Group, Gas Transmission and Metering, and also Cadent Gas. So there's sort of been two overall primary objectives for this project as a whole, for all phases. So looking to define and gather the data that's necessary to facilitate repurposing of above 7 bar pipelines on both the NTS systems and the LTS systems, but also to develop the tools and processes to store, align and visualize data to facilitate sort of the integrity management and decision making that's going to take place post repurposing of our networks for hydrogen service. So if I just take you through some of the work packages that were completed in this phase. So the first work package was focused on sort of establishing the current level of information that National Grid and Cadent hold on our pipelines, and how it's stored and what does it look like, and sort of determine some of those key gaps of where we are today and where we need to get to for hydrogen service. The second work package was then looking to sort of take those key gaps and do a bit of work to establish sort of the current inline inspection technologies out there, sort of the capabilities to sort of gather that additional data that we potentially don't have today on our pipelines. And then work package 3, sort of then looking, so I guess if we start to gather a larger amount of data on our pipelines, a lot more granular level of data, it's how we're going to store that new information and sort of how we're going to integrate that into existing business systems to enable sort of asset management activities in a hydrogen network. And then finally, the work package 4 was to outline the sort of a methodology that would allow National Grid and Cadent to carry out sort of the assessments on our pipelines based on this new information, pipeline integrity data we're collecting to sort of help sort of do that assessment for potential for hydrogen repurposing. So that was a bit of an overview on the project. So I'll now hand over to Adrian for the next slide.
Thanks, Peter. Hi, everyone. Just wait for that to switch over there. Yeah, so just talking about user needs, really. We've defined the problem, obviously some of the issues with introducing hydrogen into the gas networks. So what does that translate into from a need perspective? Well, on the right-hand side there's 4 real main areas from a data perspective that are required to consider repurposing: its feasibility, operating regime, component level material property data, knowledge, enhanced understanding of pipeline anomalies and stress states because of the effects of hydrogen, and comprehensive understanding of the pipeline route. The reason for that is hydrogen has different fluid properties to natural gas, and therefore the consequence of failure needs to be re-evaluated as well. So the idea is, as part of an overall repurposing approach, they would feed into a risk assessment activity. So as part of the project, we did a lot of work into looking at what information is currently held for NTS and LTS assets. So that was focusing on National Grid and Cadence data effectively, and what can provide information to support repurposing. And the systems in place are comprehensive from an operational, maintenance and integrity management perspective. There's a lot of good information that can feed into those 4 areas that I've discussed, but understandably, these systems are focused on the threats surrounding natural gas operation. So data surrounding hydrogen sensitive anomaly types like crack-like anomalies and hard spots is limited, and very detailed material property information on the asset materials, especially in a hydrogen environment, obviously not available. Why would it be? And at the current time. The current industry codes require extensive component level hydrogen qualification of materials, and this can quickly become non-viable when considering repurposing of existing assets, especially for the higher pressure assets where there are more onerous material qualification requirements. And I think through the work we've done, this isn't going to be avoidable, but there are more efficient ways to go about collecting this information and rationalising it, and really leveraging techniques to identify and group components and materials with common characteristics from design, manufacturing, construction and operational information, and then undertaking a population-based evaluation of hydrogen damage susceptibility, really as a way to target and streamline the whole repurposing approach here. So a lot of the work was then focused on what technologies systems can we leverage to do this. Don't get me wrong, there'll still be a significant amount of data recovery, alignment and analysis required, and likely some additional data collection, but really trying to set off on the right foot here. And the last point there, I mean, it's quite clear some of the assets go back to the mid to late 1960s, that detailed component level information, material property data is likely, it is available in physical archives, but it's not readily accessible, and it's likely to be incomplete, especially for the older assets. So there's a multitude of different things going on here that we need to consider when we're looking at pulling the data.
I've lost audio there. Is it just me or anyone else?
Yeah, I've lost
Adrian as
well. Looks like you're on mute, Adrian.
Oh, apologies there. It must have just switched on. Could I have the next slide, please?
Yeah, no problem.
So I've discussed already, but during the project, key activities, first step was to define the data requirements, within the context of an overall approach to repurposing pipelines for hydrogen based on existing standards, likely future operational regimes, and the current industry hydrogen knowledge base, which is ever developing. Then we looked at the range of data sources that exist within for the NTS and LTS assets to support repurposing as part of current natural gas operations, as well as how readily accessible the information is. We looked at where established and emerging pipeline technologies can support the collection of the additional data that we need surrounding anomalies and materials to repurpose and support future integrity management activities. Identified how those technologies could be impacted by hydrogen. A lot of them are, the majority are designed for use in natural gas service. We looked at the synergies with other ongoing UK hydrogen initiatives where they can feed data into repurposing of the NTS and LTS, particularly ongoing material testing activities in hydrogen environments, which, as I've said, is going to be key to the justification. And then, as Peter said before, we looked at the optimum data management system structure to facilitate the efficient storage, alignment, and visualization of the additional and more granular data sets that are going to be needed to support repurposing. So it's all well and good recovering this data, but it needs to be structured to facilitate efficient integrity management decision making. And the last thing, we developed a methodology to rank the repurposing readiness of network pipelines based on future operational regime, data availability, and risk-based metrics. Apologies, I'm not quite sure. My mic keeps muting itself for some reason, but I'll keep an eye on the symbol.
Am I on the right page sheet there now, Adrian?
Next one, please. Yeah. So we looked at all these things. What did we find? Where can we go? Which direction? Well, positive all round, to be honest. I mean, the design, construction and operation of the NTS and LTS assets has generally exceeded industry best practice over the decades. This means there are a large range of archived and electronic primary and secondary data sources from throughout the life cycle available to support material characterization and identification of credible anomaly types taken into service. There are existing and emerging technologies, both in pipe and external, that can support the identification and monitoring of the additional hydrogen sensitive anomaly populations that we're going to be interested in. These technologies can also support this more efficient and intelligent approach to material property verification. So there's grouping of common materials with common characteristics to make this whole justification a lot easier. And as I said before, there is a lot of synergy with the other UK hydrogen initiatives where there are a lot of material testing activities going on in hydrogen. This project, though, will obviously baseline the actual components and materials that exist in the current system and allow rationalisation against the test work that's going on and identification of gaps. Next slide, please. We had a detailed look into data management systems. What is the most optimum and efficient way to store all of this data, to visualize it, to help decision making, we've proposed a way forward in terms of a centralized geospatial data management system to support more efficient integrity management decision making. There's some visualizations shown there in terms of overlaying multiple data sets to identify threats, data gaps in materials, etc. And the repurposing readiness tool, which we outlined in the discovery phase, can really support network pipelines in terms of overall repurposing feasibility, identification of data gaps and threats as well. So that's really a companion tool to the actual repo to support the repurposing process itself. Next slide, please. Benefits, well, repurposing of existing pipeline infrastructure is going to be key to realising the UK's energy transition ambitions. Considering 25-kilometre length of new pipelines, 200 to 400 million, we've got around £6.5 billion of current assets that are paid for. So there's a key driver here in terms of reusing the infrastructure we've already got. And obviously it brings environmental benefits as well, from that perspective. Efficient data collection and management as well, and the framework surrounding them are a real key input into the viability of repurposing. So not only recovering, but organising data as well to make efficient decisions with. The level of information, the detail that's needed to justify is going to require very efficient organisation of information. So it's a key enabler to the whole repurposing activities going on. The approach that we've proposed for data collection and data management will promote more streamlined repurposing across assets with common characteristics. So we can apply material knowledge from one system to the other. We can scale it up, scale it down, and even start to look at transferring it to wider global oil and gas network infrastructure. It really is going to be a materials and anomaly database there. And as I said before, the output of this project, the data collection, should really be used to shape hydrogen qualification activities being undertaken across other UK initiatives, because we're going to really build up this vast knowledge of materials across the network components and really then allow the identification of where do we actually need to perform hydrogen qualifications testing to substantiate materials as well. Okay, I'll hand back over to Peter.
Thanks, Adrian. So yes, go for the plans for Alpha now. So this project will be progressing to Alpha. Guess the sort of main focus for the Alpha stage really is building on sort of the key findings and the approaches that have been defined in the discovery phase, and then looking to pilot some of those approaches on sort of a specific sort of section of the network, whilst also looking to start applying for live trials in the beta phase. So if I just run through some of the main sort of activities that we're looking to complete in the next phase. As I've mentioned, sort of looking to pilot population-based data collection activity against sort of a selected NTS feeder. So this will involve sort of like data gathering exercise for a specific section of the network that is likely to be sort of an early candidate for hydrogen repurposing, and then sort of looking at, again, within the approach that's been defined in the discovery phase, is that gap analysis for what we currently have against what extra information we're going to need, and then sort of build on that as well, identifying the options that are available to close out any of those identified data gaps. So that's new inspection techniques, technologies, and different analysis. And it's looking at sort of closing those data gaps, and then sort of what's really important as well, touching on the data management system, is developing sort of a bit of a roadmap for how data systems are developing within ourselves, National Grid and Cadent, and making sure that any data management system is able to integrate within the business and it's suitable for gathering the data that's collected during that pilot exercise, and then also testing the methodology of sort of that hydrogen conversion readiness assessment that was developed in the discovery phase, and sort of testing that against it, making sure it's suitable, and it also links to the data management system. And then, as I touched on earlier, then it's important then to start thinking about the plan for the beta phase in terms of sort of conducting live inspections or testing on that section of feeder, and then sort of coming to a conclusion on the likely costs and timelines for that exercise. So really that's a summary of the plans for the alpha phase of this project. So I look forward to any questions you may have. Thanks very much.
Great, thanks a lot. I'll invite everyone who's presented over the last few projects to rejoin them. If you could all just put your cameras on, that'd be great. We haven't got many questions in the chat, but I started with one for the gas analyzer system project, and actually as we move through the others, I think this kind of applies to all of them, where it feels like there's an opportunity whilst new data capture mechanisms are being considered and data architectures to ensure there is the interoperability that was talked about in the digital twin projects earlier. And I was just wondering if there's been any conversations about how you link up the various initiatives.
So I think from the sort of the gas analysis and hydrometering SIF perspective for the alpha phase, that's one of the key sort of focuses for us, is the end-to-end design work package that we mentioned. That's all about making sure that not only does it build on sort of the systems that are in place today on the network and sort of what extra information we're going to need or systems we need to handle that extra data, but it's how do we link up with other existing innovation projects that happen, like you mentioned, the digital twin. So whilst not had those exact conversations yet, that's something that I think we'll have to bring into that project to make sure that it's all aligned.
As Sarah's pointed out in the chat, recommended joining the Digital Twin Hub webinars. I think they have brief touch points on a frequent basis to talk about initiatives, not just in the energy sector, but across all as well. On the hydrometering project, I was wondering, this is quite a basic question, but what is metering taking place before or after deblending? Well, blending, I guess, both sides.
It's a good question. I'm not sure that's been defined as of yet, but I think what we'll look at is both cases there. I think there's a separate deblending SIF project going on, which probably is a better place to ask that question. But I think we certainly have in mind the different before and after use cases to look at as part of the project.
And on a related point, I was wondering, does that then impact future pricing signals? Is there a chance that rather than having a price per gas volume, that the value is different depending on which density of gases you're getting come through? Yeah,
it could be, and it's something we want to again look at in the alpha phase under the commercial module to just see what those signals could actually be, what differences they could be, what different scenarios they could be, and therefore how the measurement system in totality could support the decision makers, seeing that as soon as possible and making sure that's disseminated to the industry where applicable.
Another question I had on the metering project is with the smart metering program, I think they started only just now we start to see the use cases of third parties using some of the data rather than just the core industry functions of it. Is that something that you'd consider in design of the projects at an earlier stage? And do you have any idea who those potential future users could be?
Yeah, it is definitely. So what going into a bit of detail in the end-to-end system, we talked about mapping out the data that the system gives now under natural gas, what that would need to look like under hydrogen, and then where that data would go. So we talked about data lakes, the cloud, all that kind of stuff. So that actually, you can then, I guess, provide that to industry and the different stakeholders to improve transparency of data and how the network's managed and run and all that kind of stuff. In terms of who would use that, I wouldn't be able to answer that just yet. But I'd imagine, you know, shippers, suppliers, regulators, etc., would have, you know, a keen eye on that data. Energy consultants, all that sort of usual bodies of work. So yeah, that's certainly something we've got in mind, which could be quite a powerful output of what we do in the next phase.
And to all projects, really, and maybe to the partners who aren't in national grids, is presumably a lot of countries are looking at all these problems at the moment as well. Are we just further ahead than others, or are there other places that have tackled some of these issues already?
I'll answer that from the perspective of the dataset project. The very little, you know, completed repurposing of pipelines, or, you know, natural gas pipelines globally. There are a handful of examples, but they tend to be very specific, short length, lower pressure stuff. Nothing really that analogous to the NTS, for example, the higher pressure lines. And as we talked about before, obviously, the pressures to, you know, the pressures to achieve the same energy are going to be similar to what's in the system now. It's not as though we're going to be transporting at very low pressures with hydrogen. So, yeah, it's really pushing the boundaries in terms of mapping out an approach to be able to do this, where the data can come from, what you can leverage that's already exists, and what else that you need to collect, and that in itself will drive technology development as well throughout. It's very early days from that perspective.
Got it.
We had a contact from France, from Gas de France, that they were quite interested in what we were doing, and so weren't quite as advanced as they are in the UK.
Noted. We've just got one more. Go on, Claire.
Yeah, I'll just add a comment. I mean, I have colleagues particularly in the Netherlands and in Norway, and I think, you know, across Europe there is a move certainly to look at hydrogen, and to some extent in North America. Some of our other global areas less so. But I think our test facility at Spade Adam, in terms of the ability to test, particularly at high pressures on hydrogen, is fairly unique. So certainly within our business, I don't think there's elsewhere in Europe where we've got anything like that, where that kind of testing could be done, particularly at the high pressure range. So I think probably in the UK, from what I understand, we are probably leading edge in that kind of testing, I think.
Great, it's good to hear an opportunity to get ahead of the curve. Peter, there's just been a flag from David Mason in the chat to touch base with him, if you're happy to do that.
Yeah, definitely. Yeah.
If there aren't any other questions, we're running into the break already. So thank you all for presenting, and we'll come back for the final session in about 10 minutes time.
Thank you.
Thank you.
Thanks.
So we'll come back at 2:25. David, could you put the holding slide up for me?
Yeah.
Hi, David. Are you ready to start again?
I am.
Excellent. If you want to flick it back through the slides.
Have you got that, Chris?
Yeah.
Working? Yeah, great. Okay, welcome back, everyone. So we've just got a couple more projects to finish off the day today. I hope your energy levels are maintaining right the way into the afternoon. The first project we've got is from Northern Gas Networks, looking at thermal imagery analysis and condition assessments, fluid and pressure. As before, we'll have a question and answer session after the two projects. So please do throw in some questions, anything from sort of technical details right the way to regulatory and policy considerations are all open for discussion. So please do share them. Nick, are you ready?
Yeah, I David, can you hear me?
Yeah, I got you. Over to you.
Perfect. So good afternoon, everybody. My name's Nick Smith. I'm the Operational Innovation Lead at Northern Gas Networks. I've been project managing the thermal imagery analysis discovery phase on behalf of NGN, alongside my colleague Simon Langdale from Innovate. If you could just move to the next slide, please. And the next one again, please. So the discovery phase for this project were really born out of the back of an NIA project that we completed in March earlier this year, which was the Leak Vision project. Again, that were completed with Simplified and Innovate. So what that was developing a robotic platform that we could put into a live distribution main to analyse gas escapes, gas leakage and points of interest, to then make more calculated decisions in terms of how we'd either repair or remediate those issues. What we were looking to do with the discovery phase was to kind of take that technology to the next level and really put it to target some specific use cases. So the problem that we identified throughout the discovery phase, or that we took into the discovery phase, should I say, is that obviously methane leakage and future hydrogen leakage is a real risk to the environment and obviously public safety when we're looking to carry out any future transition activities. Clearly, there's the existing risk as well with methane leakage on the networks today. That's on the distribution and transmission networks. So again, Leak Vision were really built to really target those areas and enable operations on a day-to-day basis to operate more efficiently, reducing customer disruption and obviously reducing the impact on the environment. One of the specific use cases that we were trying to examine during discovery was the issues associated with legacy PE. So PE were first installed on the networks around the mid-1970s. The techniques, quality of fittings, quality of components has really come on since then, as you can probably imagine, but there is some concerns around potential issues when moving to a hydrogen future. Those issues are largely unknown at this point due to not having technology and the techniques to actually validate the condition of that asset with the use of hydrogen, clearly, as we move forward. So that's really what we're looking to target with Leak Vision and try and identify what the opportunity space was there. What the guys and the team at Innovate had managed to do up to this point was create a system and an algorithm whereby we could almost put a red, amber, green status on defects and on items of interest in the mains. So what we're looking to do is, again, take that technology and that methodology further forward to target specific use cases, put a cost benefit on those, and then look to move forward into future phases to actually deploy it onto the networks at larger scale. Don't know if I've missed anything there, Simon, if you just want to jump in, buddy.
No, thank you, Nick. Next slide, please. Perfect, thanks. So how the technology works that we developed, we have a thermal imagery system with a gas exciter. We effectively excite the gas within the pipe, and we're able to then see and visualize where that gas leaks from. So we're able to look at things like the types of defects in the pipe that are leaking, the population, the density, the exact internal location of those defects. We're also able to estimate the size of the leakage as well through those defects. So that's all really important information when we're considering, as Nick had said, moving to net zero, minimising current methane emissions and what that means for abatement and net zero targets, but also looking for what that means from a risk perspective for hydrogen operation of pipelines and operational efficiency if we come to do a transition, and we need to make sure that the pipes and the network is fit for hydrogen, hopefully ahead of time, to make sure that that swift switchover can be done effectively. The kind of key aims of the project are to do leakage detection and repair and really strategically target what is a global challenge in leakage detection and repair costs. These are typically high, as reported by the IEA, the International Energy Association, and they are high kind of irrespective of where you are as well. Typically, highly populated areas are a little bit higher. In the UK, it's often called escape, location and repair as well. Like I said, we want to enhance the operational efficiency for the switchovers, minimise network leakage and support H2 conversion. Next slide, please. Thank you. So, discovery review, what did we do? We looked at some typical problem definitions, so looked at the problem space that the technology can support. We facilitated common understanding amongst the industry shareholders, stakeholders, all the different sectoral crossovers, kind of key people in industry. We identified the constraints and assumptions and the use cases specifically that we could get from the technology, and then we quantified the benefits case against those use cases as well. We then selected the riskiest assumptions that we had within the portfolio to evaluate within the alpha stage project bid that we put together. Next slide. Thank you. And what we found is those use cases and problem statements typically cover three main kind of pillars. They're leakage detection and repair in its various guises, digitalisation and hydrogen conversion. Next slide, please. So in terms of user needs, we spent a lot of time working with the guys in the field, and we've been very fortunate to get really good access across Northern Gas. So different teams looking at their asset strategy, looking at the operational side of the business, looking at what they're doing for a lot of their hydrogen work with the H21 and how that crosses over with the other various schemes that are in place. And we've been able to then really kind of test a lot of the assumptions and understand where maybe some of the larger risks sit and what we need to be doing in the project going forward to make sure that we can attack those appropriately. Next slide, please. So how we worked, it was generally a really, really good project, this. A lot of challenges with the 2-month timeline. I think that was the main kind of risk that we'd had on our risk register, but it was very successful in terms of cramming everything in, really. To do the stakeholder piece, we run several industry events, networking seminars, and a really successful questionnaire to gather a lot of feedback and information. We put together a successful world gas paper so we can present this to a global audience and make sure that we're getting the right kind of feed from a much wider audience than even just the UK. We've done some showcasing demonstrations and we've had detailed discussions and a number of meeting and calls and other bits and pieces to support that as well. We spent a lot of time doing research in this project and a lot of time trying to build up a costing model that supports the project, the assumptions and the use cases that we've got. And we've tried to baseline those against what we forecast is going to be the current operational model for a lot of the scenarios that we're expecting. And we've used the best available green book approach that we can to then look at the difference that we can get through the technology, the digitalisation and the new sensing and data for leakage to then give us estimates and kind of an envelope of what we believe that the benefits case will be from a socio-economic cost perspective, a cost of carbon, a carbon credit perspective, an operational perspective, and then a little bit of a fuzzy approach to what we believe those wider economic, societal and customer benefits will be as well. We use these to then develop a net present value determination to kind of assess what we thought the shape of the solution would be and where we think some of the real benefits are in driving this forward. Next slide, please. And I'll let Nick come in if he wants to kind of talk through the main benefits.
Yeah, so the key thing that we identified throughout discovery was that there's multiple benefits across the board, not only from putting it to use today on the networks as we know it, but obviously into the future. how we do that hydrogen conversion, if we do the hydrogen conversion, and then even further into actual day-to-day operations at that point as well. So for the operational benefits that we can look to achieve today, it really is around that targeted leakage detection and repair aspect. So being able to pinpoint gas escapes and issues quicker, changing the ways of working in the sense of how we excavate down on to repair, to carry out repairs, targeting those specific areas of high traffic, you know, city centre locations. The ability really is to then reduce our customer disruption overall. Clearly, also by reducing our excavation sizes, the type of plant that we need on site to carry out those excavations, you've got really that whole scale reduction in emissions, and obviously the costs associated with that as well. In terms of that sort of interim period, there's the ability to consider using the likes of leak vision and similar technology to inform better investment decisions in terms of the REPEX programme, been able to really target areas of the network that are prone to leakage that may not particularly be considered under the current replacement programme for GD2, but then looking for how we can inform that programme better within GD3. That's really where the common understanding piece within Discovery came into its own. The ability to speak with some of the different networks, some of the different operators, and understand what their key priorities were, what they saw as problems compared to what Northern Gas see as problems, and then how we can really steer the project in a way that that's able to capture all of those issues and try and come to some sort of common goal and common direction. Clearly, if we can try and increase and improve the efficiency at which we can carry out a REPEX programme, you've then got the commercial benefits not only for the businesses and the operators, but obviously then the reduction on consumer bills as well there. You've then got the hydrogen conversion aspect, which is looking at the network again today and being able to validate the condition of the network against what we consider it may need to be like for a hydrogen operation. So again, looking at today's network, you've got metallic and plastic, or PE. Those are the two main food groups, as we call them. The difficulty that we've got is that due to the type of construction of PE, the different types of materials and assets within the ground, we need to be able to validate that every single bit of that is absolutely safe to be used with hydrogen, obviously as part of the transporter safety cases. So being able to use this technology to validate parts of the network, you know, there's the potential to reduce costs by not needing to replace all the network, not needing to replace specific parts of the network, but you've then also got to consider the early conversions. So if you look at industrial clusters, if you could use the likes of leak vision and similar technologies to validate that part of the network to enable a quicker and more efficient conversion for the high emission areas, it doesn't take the pressure off, but it allows for a good strategy to be built to enable that in a more efficient manner. And that's really what we're looking to achieve through Discovery, is to try and put a cost benefit on that. Clearly, it's difficult because there's a lot of assumptions and a lot of risks at this point in terms of the hydrogen conversion, you know, and whether that will or won't happen. So a lot of the numbers are a relatively wide scale, but the ability is that as we gain more understanding by using this sort of technology on more occasions, it really does help to narrow those costs down to a more accurate figure, I'd say. Next slide, please. So I don't know if you want to jump in on this, Simon.
Sure thing, yeah. So looking ahead, what we're going to do in the next kind of stages is really target the problem statements and use cases to develop go-to-market strategies. So kind of what that means is we're going to focus a little bit more on the specific use cases that we've come up with and the specific value propositions and benefits cases that they have, whether that's operational hydrogen, leakage detection for hydrogen, or leakage detection for methane to reduce and get to net zero. We've highlighted key risks for our Alpha project, and we're looking to test a lot of those risks and test a lot of the route that we have to get in this commercial product to make sure that then within the beta, we have a very well-defined risk assessed plan that we can work through systematically to get to this strategic aim. Next slide. Thank you. So immediately in front of us, we've got the Alpha bid that we're just submitting, and then we're looking to develop a beta stage plan We're also planning broader stage engagement, looking at other technical people that we can bring in, policy, local government and internationalisation. So we're very fortunate to be going to World Gas later in the week to go and present there and to make sure that we can get some dissemination of the technology across the globe and across the kind of academic boundary as well. And that's it from us. Contact details there. Thank you very much for the time.
Thank you both. I'm actually drinking from my Northern Gas Networks mug from LCNI 2018 or something today. Other Energy Network branded mugs are available, of course. We'll move on to the next and final project before going into the Q&As, but thank you both. So, Matt and team.
Hello.
If you're ready, I'll hand over to you for the digital platform for leakage analytics product.
Can you hear me okay? Volume okay?
Yeah, that's fine.
Great. So can we have the next slide, please? So hi everyone, I'm Matt Marshall. I'm a net zero planner representing Cadent Gas today. And I'm really grateful to be joined by Magali and Amir from Guidehouse. Next slide, please. So over the next 15 minutes, we'll take you through the background and problem statement and try and add some context to explain why we believe this is such an important and relevant project. Then we'll move on to the project outputs and what we've identified already, finishing off by looking at what the next steps are. Next slide, please. So in the UK, distribution networks currently use a single agreed methodology and leakage model to calculate emissions from the gas transportation network. The model takes real-life asset data and couples this with scientifically ratified leakage rates. So as an example, for low-pressure mains, all pipes of a particular material and diameter will leak at the same rate regardless of known condition, age and location. And there are several limitations with the current methodology. The first that I've just touched on already is that the leakage rates are static. And whilst we do use real-life asset data, the emissions from these are modelled. This limits the opportunities for including emissions reduction in any asset investment decision making and doesn't directly drive targeted intervention behaviours. We can see from this then that if we better understand real-time emissions, we can then form considered emission reduction plans. The second limitation is the scope of the current leakage model, which is limited to modelling emissions for just natural gas. It doesn't include any methods for calculating emissions from blended or full hydrogen systems. So for the current methodology to remain relevant into the future, it would need refreshment anyway as the energy landscape changes. Now, on the slide in front of you, I wanted to draw out a couple of the facts. The 129 million. So this is the cost of the UK distribution network's emissions for the financial year 21-22, and this forms part of the customer bill. And then the second one is the 30%. So this will be familiar to most. This is the COP26 2013 methane emission reduction targets pledged by the 110 countries. Now, just from those two facts alone, we can start to understand the importance of improving accuracy in our emissions estimations and then the importance of acting on them. So these changes will allow distribution networks to expedite reductions in our environmental impacts and also reduce our impact on customer bills. So it's clear to see that as technology advances and global environment evolves, that it's the right time to investigate and apply these new opportunities for improved understanding and measurement. Next slide, please. So if I could just hand over to Magali now.
Thank you, Matt. Yeah, so following on from that, I'm going to talk you all through what we kind of covered in the discovery phase. So the aim of discovery phase was to kind of assess the feasibility and develop the concept for DPLA, what we're calling the Digital Platform for Leakage Analytics. So the idea for this platform is that it would be something that would allow us to get a view of methane leakage at a national level from the distribution networks, and for this to be kind of dynamic and real time, as opposed to the current model, which is theoretical and updated only once a year. So that's what we were trying to achieve. So we looked at that from a kind of technical perspective, what would be needed, what would the concept be, what changes would be needed from a regulatory side, and also whether or not it's economically feasible to achieve this. So Matt just took you through the first step, which was kind of the current state of distribution leakage emissions and the kind of problem definition. The second step was technology and data assessment. So here we really wanted to scope out what technologies are available now that weren't available maybe a couple of decades ago when the current method was implemented, and how could those help us to kind of measure methane emissions from the system, how to improve the accuracy. And so we kind of benchmarked these on against certain kind of key features like the cost, the sensitivity. We looked at categorizing them in different modes, and we actually interviewed 8 providers of kind of some of these novel technologies to kind of gain a better understanding of that. The third step was the conceptual platform design. So this was really about getting together with the networks. So the project was led by Caden, but we also had SGN and National Grid gas transmission on board. So we got together in a workshop and really kind of worked through the use cases and the requirements for this platform to kind of work for them and to serve their business purposes. And we kind of were able to then define the vision for what this platform could look like in future. The fourth step was, of course, looking at this from a regulatory perspective. So as Matt mentioned, the current shrinkage and leakage model is something that the networks have to report on every year as part of their license condition. So we looked at some options for how this could be altered in future to kind of allow for this DPLA to be used instead for reporting, but also to make sure that it could be used as effectively as possible and for kind of bigger leaks to be prioritized in the network's kind of investment program. And finally, we did a business case analysis, so looking at what would be kind of the key costs to implement this all the way through to kind of full-scale rollout and deployment across all of the UK GDNs. And we looked at that through to 2050, so we'll be presenting that as well. Okay, next slide, please. Thank you. Okay, so first I'm going to talk about some of the technologies that we looked at. So we classified these based on their temporal aspect, their mode, and their technological kind of features. So on the temporal side, we classified technologies either as continuous or non-continuous. So continuous being things either like models such as like hydraulic models or measuring instruments that are installed on the network and that are always on and like taking readings every kind of few seconds. Those were kind of defined as the continuous box. And non-continuous were more technologies that you would use for kind of routine surveying of your assets to check if they're leaking, but that you kind of have to go out and use on site. They can't just be left to operate continuously. And then on the mode, in terms of how these are actually deployed, you have the fixed type sensors, so that would be usually the continuous ones. You have some handheld devices that operatives can kind of walk the length of your pipelines, or some sites with taking readings for methane. We can have some vehicle-based sensors which are driven around and which measure methane as they go. There are also drone-based or unmanned aerial vehicle mounted systems that are kind of really emerging in the markets now, as well as even some aircraft mounted ones. And this can be either like a small plane or a helicopter. And finally, there's the satellite methane monitoring option, which was one that we had kind of scoped out and in the application phase as being potentially really interesting, because obviously it can see things from such a kind of high scale that it seems like it could be really efficient And we did assess them, but we actually found that the resolution that you get from those is quite a bit too large, so it's very hard to actually pinpoint where your leaks are coming from. You get kind of these 25 by 25 meter squares that tell you something here is leaking. But yeah, we've concluded for now that at this stage they're not actually granular enough for this application. In terms of the actual technologies themselves, there's things like smart meter data, optical gas imaging devices, various kind of spectrometry based technologies, LiDAR, and then there are also some on-pipe or in-pipe sensor options which weren't assessed as part of the project because we kind of deemed that financially and practically it's not something you can really do retrospectively. These are really things that are best suited for new networks to install at the same time as your new pipes. Okay, next slide, please. Thank you. So here on the left, you have an example of what our outputs looks like for each of the technology assessments. So there was kind of a summary as well as some features like the technology readiness, costs, and some case study examples. So we had some really kind of detailed findings for each technology. And we also assessed how they performed in terms of relative to each other. So you can see the kind of size of the dots in the table on the right represent kind of the degree of sensitivity or whatever feature relative to the other kind of modes. So that was important as well. And this kind of showed us that actually different technologies are suitable for different areas of the network, and there's kind of a trade-off there, and it's not a one solution fits all type thing. So the point of the DPLA as well is that it needs to be able to bring together measurements from different kind of technologies, from different data sources, and to kind of aggregate those to give some useful insights. So next slide, please. Yeah, so going further into the concept, actually we can really see this. So on the right here is what we kind of see as the DPLA concept, where we kind of take existing data, existing hydraulic model that might be enhanced, which already gives some indication of where leaks might be. And then you overlay these with some of these more hardware-based monitoring technologies. So for above ground installations, we're recommending handheld or drone-based kind of monitoring. For pipelines in urban areas, we're recommending kind of mobile-based or drone-based. And then for rural, the same with the addition of aircrafts, because they can cover kind of more ground faster in some of those rural areas. And then this kind of, the idea is that there would be some analytical tool with some kind of machine learning algorithms overlays that combine all of this data and output not only a visual of where and how big leaks are, but also give some recommendations as to which ones should be tackled and in what priority, and what is the best course of action to kind of reduce emissions safely and quickly. So that's what we've kind of, the concept that we've come to terms with. And with the networks, we also developed these lists of user requirements and use cases that you can see on the right there. Next slide, please. Yeah, so this is obviously kind of a pretty major step change, a major positive step change in terms of how leakage reporting is done by UK GDNs. And so with that, we expect that some regulatory change will be needed. So we identified kind of 4 feasible options that kind of range in terms of how drastic they are. So from 1 to 4, 1 being you kind of keep as you are and you just keep using the current model that Matt talked about earlier, and you're making kind of small changes but not significant ones, and they're difficult to measure and verify. And then this increases kind of in kind of the level of change through options 2, 3, and 4, where we'd look at some possible options where the networks could be incentivized or awarded to kind of develop the best strategies to reduce emissions in some way, and to varying levels. So these will be further evaluated in the alpha phase. Next slide, please. Finally, yes, this was a really important piece that we dedicated quite a bit of time developing, because we really wanted to show kind of the value that this could deliver both to consumers and also to society as a whole. So like Matt mentioned, the costs of shrinkage and leakage gas are currently socialized to consumers. And so here we've kind of shown that by kind of reducing those emissions faster compared to what is currently business as usual, the project would deliver £542 million in cumulative benefits through to 2050, and that includes directly the benefit to consumers through reduced bills, through reduced shrinkage and leakage gas costs, but also the cost of carbon that is avoided, because of course these methane emissions have a significant greenhouse warming effect significance as well. And you can see that as well through the expected reduction in equivalent carbon dioxide emissions of around 10 million tons through to 2050. So there's some really big benefits to be found there. And these were the ones that we quantified, but there are others that we also qualified that this platform could deliver. Things like improved health and safety, because if you can find more leaks earlier, you're kind of reducing the risk of kind of critical incidents on the system. There's reputational advantages for the networks to be seen to be tackling these emissions head on. Reduced disruption for customers if we can pinpoint leaks accurately straight away, rather than having to spend more time searching and digging up roads to find the exact location of the leak, and other small things like fire hazard prevention and operational advantages. Next slide, please. Okay, yeah, and now I'll just hand back to Matt to talk you through what we're planning for the next steps in the alpha phase.
Thanks, Magali. So the alpha phase is an opportunity for solution design and trialing and understanding technologies, which, if successful, would lead to a beta phase covering solution build, before finally reaching our business as usual final product. This would complete with the rollout of a new real-time emissions identification platform, providing us with much greater opportunity to proactively reduce emissions, but also giving industry confidence that we are estimating volumes correctly. Shortly, you'll see the alpha phase is broken down into 6 well thought out work delivery packages, and I'll talk about them in a moment or two. But as a quick overview, the alpha phase would engage providers to understand suitability of technologies for the analytics platform. So looking at cost constraints, suitability and availability, production of detailed use cases and requirements, develop the detailed solution design, further refine and really understand the detail of the business case, proactively engage with Ofgem on the regulatory framework and involve with the relevant stakeholder groups, and finally develop the trial design for the beta phase. So as part of the discovery phase, we took some time to consider the eventual output and the business as usual activities post deployment, and we identified some key considerations to ensure success. And one of the main ones was reporting and regulatory alignment across distribution networks of any proposed solution design. Remembering that, as we said earlier, all distribution networks report using the same methodology currently. So that's why we're really pleased that the project is now supported not just by National Grid and SGM, but we've widened to include Wales and West and Northern Gas networks within the alpha stage application. And I think to me, this demonstrates the importance and relevance of the project. And it's great to have all the main organisation this applies to, all involved, influencing and inputting. It also means that we can be sure that the future digital platform for leakage analytics is suitable for UK rollout across the distribution network geographies. Next slide, please. So finally, this is a breakdown of the proposed project plan and details the 6 work packages I mentioned earlier. with multiple packages working in parallel during the 6-month window. So work package 1, commercial. So this is looking at commercial design options and refining the business case. Work package 2, the digital platform and analytics design. So there's a lot of work in this work package, and it involves vendor engagement and demos, understanding platform requirements, assessment of the current system landscape, and developing requirements for an enhanced hydraulic model. Work package 3, so technical options, selection and feasibility. This is about developing case studies, understanding business model options, and defining data collection requirements for each technology type. We've got work package 4, which is change. So this is looking at developing regulatory change options and recommendations. We'll also look at the preferred option for changing the current leakage model. Work package 5, which is stakeholder engagement and knowledge sharing. So this is all about engagement with the key stakeholders, customers and forums to understand the implications of any change and share learning. And then work package 6, project management. So you can see that from the slide, the phasing for each of the work packages, and these will involve subject matter experts across Cadent, Guidehouse and the other partners to ensure maximum benefit and learning. Next slide, please. So that brings to the end the presentation on the digital platform for leakage analytics. Thank you for listening, and thanks for Magley for your support.
Thanks, Matt. Thanks, Magley. If I could get the previous project to join now, and we'll wrap up with the Q&A. So we've got one question in the chat already. I think this applies for both projects. And Simon said it is likely that new hardware and methodologies for leak detection will mean that more leaks are found in the gas network. Might they be overwhelmed by the amount of work that this generates? Has there been an estimation of the number of additional leaks that have been estimated? Does more leaks equal more personnel? Who'd like to pick that one up?
If I take that for the DPLA side of things, so absolutely, you're absolutely right. That's something that we've considered and thought through in the discovery phase. And we looked at both upside and downside, right? So whether you'd observe less leaks, but that's probably unlikely, and whether you'd observe more leaks. In terms of the business modeling itself, we made an assumption that total RepEx expenditure on an annualized basis will remain constant, and you just prioritize within that existing work stack. But through Alpha, we want to use the change work stream to really delve into more, what does that mean from a change perspective? If we do get more leaks, would we increase the level of CapEx to reduce the overall number of leaks? Would we target super emitters? What types of change will be required around the safety and environmental thresholds for this to make this work? So really good point. More work to be done in that space in Alpha.
Would anyone else like to respond to it?
So I guess from our perspective, it's very similar in terms of that space is still, it's unquantified. There's still a lot more work to do to actually nail down what that looks like. In terms of how we look to deploy certainly leak vision and similar technologies today, it's still using standard and traditional response methods from the gas networks. So a member of the public reports a gas escape, an emergency engineer will go out and secure and locate the escape and program it and categorize it. Then it's the future aspects of that in terms of actually then getting to site, deploying the robot to then actually pinpoint where the escape is and reducing that response time once it's been categorized and pinpointed. Clearly at this point that wouldn't then increase the number of escapes. It'd reduce the time it takes to respond to them, meaning that we could actually respond to more if it works on that productivity basis. But certainly moving forward, if we look to proactively use leak vision and the likes to seek out more leakage on the network, clearly there will be an impact on resourcing, which in my own personal opinion I don't think is a bad problem to have in terms of looking to reduce emissions proactively. So I think it's a good problem to have in reality.
Got it. And so it's been my understanding that there's already a good number of leaks which are known of, but it's just not economic to fix them at the moment. Firstly, correct me if I'm wrong, but what I'm thinking is if you can put a value on leakage and say if you can bring identification and fix below this cost, could you not just do a sort of Google X Prize type thing and say 50 million to whoever solves this problem?
Yeah, and that's part of the work that we're doing. So the Leak Vision kind of robot that we've got on the push rod technology, it's ubiquitous across the gas industry in a standard CCTV format at the moment for something called the 3030 replacement program. It's very widely used, our technology there, to enhance productivity. And we're looking at the total package of the overall strategic cost of identification of leakage and the reduction of the costs associated with that repair. That's really important for us to get to a situation where we can minimise leaks. Using our kind of transfer from the water sector, we work on water as well. They target leakage below economic value, and they have been doing for a few years now. We found that one of the gaps in why we've not really got there is just because finding leaks on water is typically a little bit easier because they emit noise. So there's lots of tools and techniques that the guys in the field have to be able to target that at the moment. And at the minute, we don't have anything like that in the gas space because of the low pressure gas that we ship in distribution.
Would anyone else like to touch on that?
Yeah, I'm happy to add something. So from our perspective, like you said, let's say you have a limited kind of pot of money for repairs in any 1 year. With the current model and method that's used to report, all leaks are kind of treated as equal from an emissions perspective. Whereas with the DPLA, the idea would be that we could find kind of the higher rate leaks, what we've been referring to as super emitters, and various studies have shown that these super emitters usually represent about 5% of total leaks on your system, but 35% roughly of your total emissions. So if you're able to know where those are and to prioritize like where your money goes to solve those first, then obviously that will have huge benefits for kind of carbon emissions in the short term.
Got it. And Simon, related to your point, is there anything around coordinating some of these works with other utilities? Does that happen at the moment? If you're going to dig up a road, is there any correlation between water leakages and gas leakages?
There's not a particularly large amount of integration at the minute, but we work really closely with a lot of academic institutions. So we're looking at bringing in a very notable underground robotics institution on our next phase. We also know that Birmingham are running a programme to try and coordinate a lot of that underground infrastructure work, because once the surface of the road has been broken into, it's never the same again. So if you're going to access the road to do a gas repair, why not make sure that you can plan in all the water repairs and the cable tools and things you need to use at the same time? So I know that there's work going on in that space. It's just not something that we've coordinated heavily with at this stage.
And on that, we've been working with the Northumbria Water Festival to try and get some cross-sector work in there. So if anybody's interested, touch base, and we're hoping that we'll have a bit of water representation at the Energy Innovation Summit in September as well.
Perfect, yeah, that'd be great.
If there are no more questions, I've got a few slides to wrap up, but I'd just like to say thank you to both of your projects as well. In particular, it was really good to see the identification of potential regulatory change requirements in future. I think part of the SIF is about identifying these at an early stage so that they can be worked on and resolved before the end of the beta phase. So that was great to see. Thank you all. So I've just got a few points to cover to wrap up. There are a few other show and tell sessions still coming up. We've got a data and digitalisation session, the final one looking at weather and predictive analytics. That's on Monday, 9 to 11:30. And then we'll be doing the whole system projects again on Monday, looking at flexibility and whole system integration. So if you're interested in them, I think there's going to be a few fascinating bits of information coming through there. Registration page will be shared in the chat. And then the last point is just to highlight that the round 2 challenges are now open for ideas. These are around 4 areas that build on the round 1 challenges. We're focused on supporting a just energy transition, preparing for a net zero power system, improving energy system resilience and robustness, and accelerating decarbonisation of major demands. And the 3rd-party launch event will be happening for them next Wednesday. And please do share the registration to that with all of your networks to get it out on LinkedIn. Let's spread the call far and wide and get some really great ideas coming to the networks as well next year. So that's all for this session. Thank you all very much. Appreciate your time on the Friday. I feel like I've done about a term's worth of learning in one day. So it's been really fascinating hearing about the projects, and thank you all for putting so much effort in over such a short period of time.
Thank you. Thanks for organising.